The PathwayBench research paper introduces a novel benchmark for assessing the routability of pedestrian pathway networks inferred from multi-city imagery. This benchmark addresses the challenges of extracting accurate, routable paths from remote sensing inputs, particularly for pedestrian paths that are narrower, more frequently disconnected, and variable in smaller areas compared to roads. The dataset includes regions from 3 cities, featuring co-registered aerial imagery, road networks, and human-validated pedestrian pathways. The evaluation procedure emphasizes graph connectivity and introduces a new metric of local traversability as an efficient proxy for global graph routability, focusing on the traveler experience. The paper contributes a human-validated ground truth pathway graph, evaluation criteria emphasizing graph connectivity, and an evaluation of state-of-the-art methods for the pedestrian pathway extraction problem, demonstrating the exposure of unique challenges and quality issues that correlate with downstream utility. The research focuses on enhancing the accuracy of pedestrian pathway graphs by integrating multiple data sources and novel evaluation metrics. It begins with the PathwayBench dataset, which offers diverse imagery and annotations from various geographic areas. The concept of routability is emphasized, highlighting the need for measuring local and global routability. Local routability is evaluated through polygon-based metrics, such as degree centrality, betweenus centrality, and traversability, which assess the ability to travel through small intersection-scale regions. The research defines a pedestrian graph and a polygon graph, emphasizing the importance of terminating nodes and their intersections with boundaries. The concept of polygon traversability is introduced, focusing on the ability to navigate from one boundary of a polygon to another. A novel metric is proposed, comparing the sets of traversable boundary pairs for a polygon from each graph using Jacquard similarity. The implementation involves partitioning the test area into tessellating intersection polygons, TIPs, enabling efficient computation of local connectivity metrics. Experiments show that using both aerial satellite images and street map images improves segmentation performance, particularly in removing spurious predictions and recovering occluded sidewalks. The evaluation results are summarized in Table 2, demonstrating the importance of using graph-level metrics in evaluating pedestrian graph prediction models. Here is the combined summary. The PathwayBench benchmark provides a comprehensive evaluation mechanism for extracting pedestrian pathways from aerial imagery, addressing inconsistencies in datasets and metrics used in the literature. It comprises 5 co-registered features and a suite of metrics tailored to assess the structure of the graph, ensuring routability properties for downstream applications. The evaluation focuses on the experience of travelers, highlighting strengths and limitations of existing methods obscured by conventional pixel-wise evaluations and simple edge-counting approaches. The profit models, particularly those utilizing the VID architecture, demonstrate better performance in graph routability, achieving the highest traversability similarity values among the evaluated models. This underscores the importance of considering how travelers navigate the environment, as the F1 score alone may not reflect practical requirements for real-world routing and navigation tasks. Research on high-definition maps and road network extraction from various sources, including remote sensing images and crowdsourced GPS data, is presented. The HD Map Gen model generates hierarchical graphs of high-definition maps, while studies on sidewalk extraction use aerial and street view images. Road network extraction from very high-resolution remote sensing images is also discussed, utilizing OpenStreetMap as benchmarks. The importance of unbiased datasets is highlighted, and the need for predictive equity in object detection is emphasized. The creation of annotated datasets for learning urban pedestrian path networks and collecting sidewalk network data at scale are discussed. The FUNet network is introduced, which fuses location data and remote sensing imagery for road extraction. This research showcases advancements in creating and utilizing high-definition maps and road networks, highlighting the significance of diverse data sources and unbiased methodologies.